look at this. This, for a value of 3/10 plus 6/10 times odd, you get this set. The black part is actually the Julia set, and the colors come from measuring the distance away from it. This is remarkable. Not only is it very beautiful, but it has a remarkable property. If you take a little piece of it and blow it up, it looks pretty much like what you started with. And you take a little piece of that and blow it up much more, 1,000,000 times, it still looks pretty much the same. It's an extraordinary property. That's called a fractal property. Here's another picture of the same one, and I have a couple of other Julia sets here. And still more. These are all approximately similar, but they're quite wide variations. But this is something very beautiful. It's only possible to appreciate the beauty of these Julia sets because of computer graphics. Beforehand, a century ago, Julia was able to analyze certain properties, but he never saw this picture.
It sort of also reminds you of the galaxies, you know?
Yes, yes. Things go around. And you see, if you take a little piece here and blow it up, you get more of this structure. It's, yes.
It seems to me like you talked earlier about beauty and evolution and the sort of contradiction of the fact that beauty doesn't seems unnecessary to sort of the survival thing. But it strikes me that the beauty, one of the things about beauty is symmetry.
Yes.
You see symmetry here, you see symmetry in faces and so on. And it just made me think earlier that symmetry might relate to sort of health and fitness when it comes to evolution
certainly.
as well. And so it's just
That's
reminded me
certainly
of that.
true, that symmetry is an aspect of beauty that does have advantages for evolution, without any doubt. But I feel that there's so much more in it. Well, you can see all the symmetries here. They make it very lovely. Well, let's look at something else. This is the so-called golden mean. I'm going to describe what this is. This rectangle here has the right proportions to look very nice. Painters usually use approximately this proportion between the height and the width because it's very pleasant. And if you have a painting that's higher than it is wide, usually it's just this turned around 90 degrees. But what is the precise definition of the golden mean? It is if you take this rectangle and remove this square here, then what's left, if you turn it, has the same proportions. Actually, now I'm seeing something that the computer did that's not quite right. This isn't quite a square. It's a little bit compressed this way. But it should be exactly a square. In that case, this would be exactly a square, and this exactly a square. And as you keep removing them, you get this lovely spiral that goes in. Well, why? This is very interesting in itself. It has to do with the so-called Fibonacci numbers. Leonardo da Pisa, a son of Fibonacci, therefore, invented this sequence of numbers, 1, 1, 2, 3, 5, 8, 13, etc. Each number is the sum of the two preceding ones. 1, 1, 2, 3, 5, 8, 13, 22, etc. And if you look at the ratio of two of those, for example, 8 over 5, 13 divided by 8, 22 divided by 13, as you go farther out, they approach the golden mean, this distance divided by that distance. And it's very present here in the pentagram. If you look at this long interval here in the star and this shorter piece of it, the ratio is a golden mean. And if you look at this piece here divided by this smaller interval, it's the golden mean. And if you look at let me see, did I say, this piece divided by this is the golden mean, this piece divided by this is the golden mean. So it keeps coming up again and again and again in here. And if you put another smaller star inside, then you can get an infinity of golden means in there. There's a very interesting book with a whole series of things about the golden mean. Here's another symmetry that's quite lovely in arithmetic. 1 times 1 is 1, 11 times 11 is 121, 111 times 111, and so on. It's quite neat. And there are other similar things. Every once in a while on the internet I get a message giving me about half a dozen of beautiful numerical calculations like that. Then there's a nice story that I wanted to tell you. Well, the theory of numbers is very beautiful. There's an interesting anecdote about the British professor G.H. Hardy and his Indian collaborator Srinivasa Ramanujan. They were both eminent number theorists. I should just make a little aside about Hardy. He wrote a book called Pure Mathematics. And in that book, he considered it marvelous that the theory of numbers was an area of mathematics that's just beautiful in itself and would never be able to be contaminated by having applications. Well, of course, we know that nowadays cryptology is based entirely on number theory. So when you send a message through the mail or when you do something banking by email, by the internet, it's an application of number theory. So he's probably turning over in his grave about that. But Ramanujan came from India. He wrote a letter to Hardy in which he outlined several dozen ideas about number theory, assertions, affirmations. And Hardy got this letter. He didn't know who the author was. He started to look at it. And he saw some assertions that he knew, others that were false, others that were very intriguing. He didn't know whether they were true or not, and others that were extraordinarily ingenious. So he realized right away that he was reading something from one of the brightest minds in the history of mathematics. So he got into contact with Ramanujan, who was working in a government office and just did this mathematics on his own. And Hardy brought Ramanujan to England, where he became a professor. But unfortunately, he had contracted some kind of a disease, I think pneumonia or tuberculosis, and his health was already ruined. One day, Hardy went to visit Ramanujan in a hospital. And they were discussing things, and Ramanujan said that every number is interesting. And Hardy said, that's not the case. What's special about the number of the taxi cab that he had taken? Well, whoops, this didn't get done correctly. And in fact, there's an error here that John pointed out to me, a double error here. Anyway, the story is he answered immediately. This is 1729 was the smallest number that could be a sum of 2 different cubes in 2 different ways. So here's 1729. This is supposed to be 9 cubed plus 10 cubed. That's the double error. And this is 12 cubed plus 1 cubed. I don't know why the cubes got laid down, but this was an error that I made. It's 9 and 10 rather than 8 and 9. But that's amazing that Ramanujan responded this immediately. And another number theorist, Littlewood, on hearing of this, commented that every positive integer is one of Ramanujan's personal friends. I think that's a lovely story.